Hey there, physics fans, welcome back. Today I'm going to demonstrate free body diagrams for rotating objects with mass, but we're going to use textbook problem 10-92 as our example in drawing this free body diagram. If you notice, I emphasized the words rotating and mass. Up to this point, you have done pulley problems, and those pulleys, though, had a key phrase in the problem statement, and that phrase said that the pulleys were frictionless and massless. Emphasizing that massless component, therefore we could treat it as a point. We didn't have to consider the mass distributed. We never had to draw a free body diagram for the pulley. It's no longer true. We're in block 3 of the course, so things are rotating and they have mass, so therefore they have inertia. So therefore we have to account for the forces acting on those objects that are rotating. Hence why we are going to do free body diagram process, but there's some slight changes. So we'll go through all 4 steps. The steps remain the same. Isolate the body, draw and label all external forces acting on the body, choose a coordinate axes and direction of positive rotation, and then lastly, of course, include critical angles and dimensions. So here we go. We're going to execute and draw the free body diagram for 10-92. All right, physics fans, and that's step 1 of the free body diagram process. I have isolated the body. The pulley, as we saw in the text problem 10-92, consists of 2 concentric circles. I have done my best to make it very distinct between the inner circle and the outer circle. And that's so that later on in step 4, it's really easy to label my critical dimensions. All right, so with step 1 complete, I'm now going on to step 2, which is draw and label all external forces acting on the body. So I'm going to remember my wonderful mnemonic, 1 to F, which allows me to go through and remember what are all the different possible external forces that we've talked about in class that could apply here. And so I'm going to go through. The first one is W, so that's for weight. And since the pulley has mass, there is definitely a weight force being applied. And the weight force always starts from the center of mass. So in this case, it's going to be where that axle is, the axis of rotation. So I'm just going to take this ruler here and draw my weight force. And it goes straight down, and I'm labeling it M sub P, so mass of the pulley, times acceleration due to gravity, and of course remembering my vector hat. All right, so I've done the weight force, and then I'm looking at A. A is for applied forces. In this case, we're going to treat tension as tension. It is technically an applied force, but because we're dealing with ropes, we like to put it in a separate category of tension. So we have no technically applied forces. So now we have the normal force. The normal force always starts from that axis of rotation. But I'm going to wait a second. I'm going to draw my 2 tension forces first, and then I'm going to go back and draw my normal force. Now I'm going to do the 2 tension forces. So there's one tension force applied to the larger circle, one tension force applied to the smaller circle. We always draw our tension forces when we're dealing with pulleys. They're going to always be 90 degrees from the circle. They're going to be tangent to the circle. So in this case, I'm going to draw first T1. So just nice tangent pointing downward. And then I'm going to go over here and draw tension 2. Again, nice tangent to the circle pointing downward. And I've labeled my subscripts. T1 and T2 do not equal. Can't assume that they are the same value because this pulley has mass. So that is a change from previous pulley problems. Now this pulley has mass. All right, so I've labeled my 2 tension forces, and now I'm going to look at friction. Friction in this case, it is a frictionless pulley. The problem tells us that. That is an assumption unless it's told to you that the pulley has friction. You could assume, or you should be able to assume, that the pulley is frictionless. So in this case, we don't have to worry about it. Now I'm going to go back to my normal force. And I did this one, I saved it for last, because the normal force when we're dealing with an object that's rotating, in this case the pulley, the normal force will always start from the axle, and it's going to point in the direction opposite of the summation of the other forces. So I'm going to start from my axis of rotation all the way straight up, and I'm labeling it N sub P with a vector hat. Now, on some pulley problems, you may have an angle associated with it. That is an unknown theta, so that would be something you'd have to consider for step 3 of the free body diagram, but that's not the case in this problem. All right, so I've labeled all my forces. I have them clearly distinct. Now I'm going on to step 3. So I'm going to choose a coordinate axis and direction of positive rotation. So first, you're all familiar with drawing that coordinate axis. I'm just going to list out what is x and y as the direction of positive rotation. If the problem doesn't tell you that everything's going to rotate counterclockwise, pick a direction. Pick a direction to say it's positive. As long as you're consistent with this coordinate axis up here in your direction of positive rotation, when you do your math, you're going to be correct. If you're not following your coordinate axes and you start substituting in things, you have the potential to get the answer incorrect. So always pick a direction of positive rotation and follow through with your work. Make sure your work matches what you've listed up here. So I've done step 3, chosen that coordinate axis, direction of positive rotation, and now I'm going to do step 4, which is include critical angles and dimensions. So critical angles, just a reminder, those are those angles that are not 0 degrees or 90 degrees or 180 degrees, right? They're not just going in either all the y direction or all the x direction. They're going in some just off of the x or y axes. In this case, all of my forces are pointing solely in the y, so I don't have any critical angles to label. But I do have critical dimensions. So critical dimensions are those distances from the axes of rotation to the point of application of the force. So I'm going to really emphasize this axes of rotation. So I made that circle much bigger. So you can see that for my normal force of the pulley and the weight force of the pulley, they start at the axes of rotation. They don't have a critical dimension, which means there's no torque. Because we take that cross product of the critical dimension with the force that's being applied to the rotating object, and that's how you get torque. So in this case, there is no torque coming from either of these two. But our tension 1 and our tension 2, those two forces do create torque if you take that cross product. They are not completely, they do not start at the axes of rotation. They start some distance away. So that's where I'm going to draw 2 lines here, and I'm going to label them different colors to really notate and make them stand out. So I'm going from the axis of rotation to the point of application of my tension 1. And I'm going to label this R sub 1. And then I'm going to use a different color, and I'm going to do from the axes of rotation to that point of application of T2. And I'm going to label it R sub 2. Now I have clearly labeled 2 critical dimensions from the axes of rotation to the point of application of that force. And those 2 dimensions are critical for determining the torque from tension 1 and the torque from tension 2. This is why your instructor has probably emphasized a lot in class that it's not called the radius. R is not the radius. R is the distance from the axis of rotation to the point of application. In this case, it's the point of application of your force. These 2 forces, T1 and T2, well, you do the algebra, you're going to be able to solve for torque 1 and torque 2. So, all right, physics fans, that completes this video. We have gone through the free body diagram process for rotating objects with mass. We've gone through all 4 steps, the same 4 steps you've been working with, but now we're dealing with a rotating object. And we've introduced those 2 new concepts of direction of positive rotation and, of course, our critical dimensions. Good luck as you keep working on problems, and have a great day, physics fans.